Welcome to A to Z Academic. In this lecture, we will discuss about the UJT. UJT full from the Unijunction Transistor. In this lecture, we will cover basic of the UJT. What is the UJT? Then discuss the basic structure of the UJT, then symbol, and after that we will discuss about equivalent circuit of the UJT and working principle. After that we will discuss IV characteristics of UJT and overall conclusion of this lecture. First we will discuss the introduction. UJT is the three terminal based silicon based semiconductor device which also act as a switch. Actually. Why UJT? Unijunction. What is the significance? The name of the signifies that it has only one PN junction, but it is different from the diode because it has a three terminal. PN junction diode normally two terminal, but this unijunction transistor is three terminal. The UJT is a transistor, but it is quite different from the BJT and Ph.D. UJT is the single junction, but BJT is the two junction. UJT used as a sawtooth wave generator, but BJT we do not use as a sawtooth wave generator. This is the basic difference. Next we will discuss about the structure of the UJT. So first we discuss structure of the UJT. First we design this is the N-type silicon substrate, N-type lightly of silicon substrate. This N-type, this is the N-type silicon substrate, and alloy the P-type heavily doped P-type resin. Actually, this is the N-type lightly doped. This is the lightly doped silicon substrate. N-type lightly doped silicon substrate. And P-type heavily doped P-type resin. Heavily doped. This is the P-type resin alloy near about the any base terminal. This is the base terminal, two terminal. This name is this metal connected here. This name is this PN junction. This is the emitter. And N-type substrate both side is the one terminal. This is the suppose one another terminal, and this side is the connected the another terminal using metal. This is the suppose base one terminal, and this is the base two terminal. Okay, this is the base two terminal. This is the basic construction of the basic structure of the UJT. This is the UJT structure. Here notice that the emitter region actually near about the any base region. Means the base 1 to emitter region, base 1 to emitter distance is the high. This distance is the high, and this distance is the closest distance. This is actually closed to any base region. Okay, this N-type silicon substrate bar, this is the two junction in emitter to base one junction, base 2 another junction is the emitter to base 1. So base 1 to base 2 show the resistance. This is the show the some resistance because of that this is the lightly doped. So this is the behave as a one resistance. But this resistance is the two terminal, two direction. This is the emitter to base, this emitter to base 1 resistance, this is the RB1, and this portion emitter to base 2, this resistance equal to RB2. So RB1 actually emitter junction E to base 1 resistance, and RB2 1 resistance, this is the emitter junction to base 2 junction. So silicon, this UJT n type substrate, silicon substrate, total resistance, interbase resistance, this interbase resistance equal to RB1 plus RB2. This equal to, suppose we consider the RBB. This is the lead. Okay. So interbase resistance of the silicon substrate, n-type silicon substrate, their total resistance RBB. Next, we design the symbol of the UJT. Symbol of the UJT, this symbol, this is actually 3 terminal. This is the 3 terminal. This is the base. Suppose this is the base 1 terminal, and base 2 another terminal, and this emitter region. This is the emitter. This is down arrow. Emitter. This down arrow means that this current direction. Actually flow emitter to base 1 region. That current do not flow emitter to base 2 region. This is why flow the emitter to base 1 region. This is discussed in the working principle. So this is the symbol of the, this is slightly arrow direction. So this is the symbol of the UJT. This is the symbol of UJT. Okay. Next, we will draw the equivalent circuit of the UJT. So equivalent circuit of the UJT. We next will draw the equivalent circuit. This is the equivalent circuit of UJT. This is the resistance base 2. This is the base 2. This is the 1 resistance. This is the RB2. Then this resistance equal to RB1. This is the base 1 region, and this is the PN junction. This region is the actually PN junction, this portion. So that this junction, this is the PN junction actually. This PN junction. Highly doped P region, and this is the N, the lightly doped. This is the behave as a PN junction diode. This region is the emitter E, and this RB1 actually this is the variable resistance. This show the variable resistance. This is the changeable resistance. Why you change this resistance? We will discuss in the working principle. So this is the actually equivalent circuit of equivalent circuit of UJT. Okay, this is the equivalent circuit. Next we discuss the working principle from this equivalent circuit. In this, suppose first condition we consider first emitter no voltage, emitter terminal, emitter first emitter is the open, only we apply the voltage, B2 terminal to B1 terminal. Then we apply the voltage, suppose this portion, apply the positive voltage, suppose B2 at 1 voltage, apply the voltage, this voltage equal to actually VBB. This voltage apply the, suppose VBB, applying voltage VBB. Okay, and this is open, emitter open. What will happen? Emitter open means that this terminal, suppose this terminal RB, this is the RB2 and RB1. So this is the voltage gradient resistance. This portion equal to, suppose RB1 terminals resistance RB1. There will be some voltage drop, and across the RB2 also some voltage drop. First we calculate the RB1, this voltage drop, actually color, change the color in this portion, and this voltage drop, suppose we consider this voltage drop equal to V1 across the resistance RB1. So V1 voltage equal to what is the voltage across the RB1? This voltage actually equal to V1 equal to RB1 resistance by total resistance, total interface resistance. Total interface resistance RB1 plus RB2 into input voltage equal to VBB. This is actually voltage divided rule. So this voltage divided rule, so V1 equal to, we represent the eta VBB, where eta equal to this is the RB1 by RB1 plus RB2. This name is the, this eta equal to actually intrinsic stand ratio, where eta represent, eta equal to intrinsic stand of ratio, intrinsic stand of ratio. So eta equal to actually RB1 by RB1 plus RB2. So this RB1, RB2 actually this is the actually RBB, intrinsic Interbase resistance, actually total interbase resistance. Here RB, here calculate the RB equal to actually interbase resistance, RB equal to RB1 plus RB2. This is the interbase resistance. So V1 equal to this voltage. So what will be happened here? So V1 equal to this voltage eta. Suppose E open. So there is the actually reverse bias, PN junction. This is actually reverse bias. So this is V1 is the positive voltage and emitter open. N terminal is the positive voltage, in terminal is the V1 voltage, P terminal equal to 0 voltage, open with the 0 voltage. So this PN junction diode actually reverse bias. Reverse bias. So reverse bias means that there flow the only minority carrier, charge carrier only flow the minority charge carrier. So there is the one leakage current flow from P to N, means the leakage current on flow. So in this IV characteristics, we draw the IV characteristics. IV characteristic, we draw IV characteristic. I will remove few part. Here we remove few portion. Okay. Here we actually draw the IV characteristics. So IV characteristics, actually IV characteristics, we draw IV characteristics. This is the suppose this is the VE. This voltage actually represent the VE, means the emitter voltage, and this axis represent the current. So how many current here flow actually? How many current flow? I current. So in this reverse bias condition, there is the flow the only, suppose reverse bias V equal to 0. So here current flow the, suppose we consider that this current equal to this reverse current flow, this portion. V, when the V equal to 0, this current flow, this is the negative region current flow. When the voltage, emitter voltage continuously increase, when the VE voltage increase, what will be happen? Suppose initially, suppose here a table given the one table, suppose VE voltage, this is the V1 voltage. Suppose VE voltage first 0, V1 voltage, some voltage, we consider that this is the 1 volt. Suppose we consider. Then VE equal to 0.5 volt. There is this V1 is always fixed, 0.7 volt. This is the V1 also fixed, 0.9 volt. This is the also 1 volt. This is the 1 volt. This is also 1 volt. This is the 1.5 volt. What will be happen? This is the 1 volt. What will happen? 0 volt, V0, this V1 equal to suppose 1 volt. This is the reverse bias, more reverse bias. Suppose V equal to 0.5 and this is the 1 volt. This reverse bias voltage is the decrease. Reverse bias condition is the decreases, means the current will be decreased. Then suppose 0.7 volt. Suppose 0.7 volt, apply the 0.7 volt and V equal to 0.7 volt and V1 equal to 1 volt, means the there is the reverse bias continuously decreases, means the current equal to continuously decrease. And up to 1 volt, V equal to 1 volt equal to V1 also 1 volt, means the when the VE equal to emitter voltage equal to dropping voltage V1, then current will be 0. Here equal to 0. Current will be 0. So we black color here there, this is the actually current continuously decreases. So V equal to V1. V equal to V1, this is the current will be decreases. Okay. Current will be decreases. Then diode terminal is the sum. Diode is the sum cut-in voltage. Suppose the diode voltage, suppose cut-in voltage, consider the VD. VD. Suppose VE, this terminal voltage equal to actually VE, V1 plus VD. So VE less than V1 plus VD, then there is the flow the slightly current. When the V equal to V1 plus VD, their current will be constant fixed. Peak current. There will be slightly peak current. After that, when we increase the VE voltage, after that when we increase the VE voltage, suppose VE voltage greater than V1 plus VD, what will be happen? VE1 equal to, suppose VE equal to V1 greater than V1 plus VD. So this is the diode actually emitter terminal will be forward bias. Emitter terminal will be forward bias. They are equal to voltage is the this portion hole, P region is the hole is the flow, this junction portion N region. So this hole actually move from this direction. This direction means actually base 1 direction. Hole try to move the base 2 direction, this direction also, but base 2 voltage the positive voltage, hole also positive voltage, this is the hole positive, this is the actual repulsion, this direction do not any current flow. Base emitter junction to base 2 region do not any current flow, but this hole P region, emitter region is the hole and base 1 is the negative region, so this is the negative, so current flow emitter junction to this base 1 junction, current will be flow this junction. When the current flow means the carrier concentration increases the RB1 resistance, so there is the resistance will be decreases, so resistance will be decreased, also VE will be drop. V will drop to how to region? When V will drop how to region? V will drop when value point V will be drop up to value point, continuously drop this region. This region is the value point. Means after this point, this RB portion voltage do not will be decreases. Is the minimum region. After that, when the VE increase, then is the this junction will be behave as a normal PN junction diode. Normal PN junction diode characteristics. So we the summary this waveform. Summary from this waveform. Draw. It summary. This is the negative region. This is the voltage actually dropping. So we define the region name, define the region name actually. This region name is the actually cutoff region. This region name is the cutoff, is the reverse current flow. This region name cutoff region. This region only flow the reverse current, and this is the VP, is the peak voltage. VP, this is the actually peak voltage, maximum peak voltage, reverse current, maximum current. And this region, actually this region is the resistance RB1 continuously variable decreases, resistance RB1 decreases. This region actually name is the negative resistance region, negative resistance region, negative resistance region. And this reaction, this current actually, this when this behave as actually PN junction, this actually saturation region, Why saturation? This is the I voltage and current both is the voltage increases, current also increases, this increases. So this region voltage, mention the voltage, this region voltage actually, this is the VE, this region voltage equal VE less than V1 plus VD. VD actually diode voltage, cut-in voltage. Actually name is the cut-in voltage, and this region voltage is the negative resistance region, VE greater than V1 plus VD, just slightly greater than, this is the slightly greater than, and this region VE greater than V1 plus VD also increase the current, will be increase. So this is the IV characteristics, and this is the basic structure, this is the structure, this is the equivalent circuit. So we'll, from this lecture we will discuss about the what is the UJT, then we will structuring, what is the structure, then we will the equivalent circuit, then we will discuss about the IV characteristics of the UJT. This is the overall lecture. Next we discuss about the what is the application of the UJT. What is the application of the UJT? This application of the UJT, this use the trigger device for SCRs and triac. Any SCR circuit or triac circuit require the trigger voltage. In trigger portion we apply the UJT, and after that this unique application of UJT use the sawtooth wave generator, means the relaxation oscillator. This is a very important application. After that this is the timing circuit, and also we will use the phase control circuit, another application in the power electronics device. Okay. In this lecture, we prepared from the reference book Basic Electronics Engineering, author's name is Jyoti Prasad Bandyopadhyay and publisher is the Vikas publisher. Okay, thank you.